Welcome to our 2.5 discussion on the product and quotient rules. We're going to split this up into two videos, one for the product rule and one for the quotient rule. So I'll motivate the idea by completing this activity, which is available on our course webpage. It says that as we near the 2012 presidential election, it becomes increasingly more popular to discuss statistics of former elections. Suppose a statistician is reporting on voter outcome. Using statistical tools, he's able to approximate the number of U.S. citizens of voting age, people who are able to vote, by the following function, which is in hundreds of millions of people. Since he's interested in how many people actually vote, it makes sense that he wants a function that approximates the percentage of voting age individuals that actually vote. So this guy outputs the percentage of the voting age people who actually do turn up to make a vote. The first part that we're asked to do, so both of these are in terms of T years since the 2000 election. So if we plugged in 0 into both of them, they'd be the year 2000, etc., etc., etc. And now the first thing we want to do is start off by completing the following table to determine the actual number of voters in the 2000, 2004, and 2008 elections by using the results of the two functions. So I'm going to come back over here, and I've already got these two functions plugged into my y equals screen. I'll start with the first one to get my v of t values. So I want an output for 2000, 2004, 2008. So I get 2.1, 2.2, 2.3, 2.4, and now I want the percentage of voters. So 2.100 million people voted in 2000, or were of voting age, and the number of people who are of voting age is actually increasing, as we know this. Now what we will go ahead and do is we will go ahead and look at the other function and get those outputs. And so we get 0.51, we get 0.55, we get 0.57, and we get 0.585. So how do we get these numbers here? Well, this is the total number of people who can vote. Only 51% of them do vote, so we want the product. So we want 2.1 times 0.51, which gives us 1.071. Here we want 2.2 times 0.55, which gives us 1.21. And this is the number of 100 million people who actually do vote. So roughly, it's pretty close to half each time, just a little bit more as time progresses. 2.3 times 0.57 is going to be 1.311 100 million people. And 2.4 times 0.585 is going to be, whoops, 1.585. is going to be 1.404. So how are we getting these numbers? So imagine that this is for any generic year instead of for 0, 4, 8, and 12. Well, what do? We took v of t and we multiplied it by the output from p of t after we plugged in our inputs. So what does that mean? So the number of the total number of voters, which I'll abbreviate t of t, so the total is a function of time, is the number of people who can vote times the percentage of them who do. Well, we know that this is given to us, the number of people who can vote, by the function back here, 0.025t. Now I'm doing it symbolically, so this is what we would plug t into, and then we would multiply that by the percentage function, or the output from the percentage function. So negative 0.09 times 0.86 to the t plus 0.6. So there would be our function. Now we're not going to distribute or anything because look at this. We have a linear and we have an exponential. So it doesn't really make much sense to multiply them together because then we get kind of this hybridization of many, many functions together. We already have that, in fact. So part B says, or number 2 says, the statistician also would like to use 2008 data to come up with an estimate for 2012, since he knows that the model could be very inaccurate for 2012 data. So in other words, we really should not be doing this because we are extrapolating outside of our known data range. We only have data for from 2000 to 2008. We don't know what's going to happen in the 2012 election. So rather than to just say, hey, let's just use a bunch of equations that are only locally useful, we're going to try to use the rate of change in 2008 to help us predict what might happen in the future based on what's happening in 2008. So we want to find the derivative of the product in year t, in the year t row by using h equals 0.0001. So in other words, we want to estimate the instantaneous rate of change in 2008. Well, just to verify to ourselves that this function gives us the same outputs as these guys, that these totals actually come out of this, we're going to plug this new equation into our y equals, because that's really what we want. We want the total number of people. 0.025x plus 2.1, parenthesis, open parenthesis, times negative 0.09 times 0.86 to the x power plus 0.6, close parenthesis. And now we can go out to our table and notice, voila, 0, 4, 8, and 12, we get pretty close to the same answers with the exception of a little bit of rounding error. Of course, we'll use the exact numbers when we calculate the derivative, but now we have that information here. Okay, so we're going to use, remember, the old method just says pick 2 points such that one is the point of interest and the other point is very, very, very close to that point. Now when I do this, if I'm only going to do one set of ordered pairs, I want to make sure that I'm getting something like 7.9999999 or 8.0000001, and I also want to make sure that I'm rounding the outputs really far out. So in fact, this is not 1.311, it's 1.3181062. Let's just go out that far. That's really important when you do it the old-fashioned way, that you round really, really far. And then it says use h equals 0.00001, which means that we're going to use the point 8.00001, and then we got to figure out what the output is. So I'll do that very conveniently here. I'll actually just do it in my calculator. Whoops. I'll come over here and I'll type in 8.0, 4 zeros, and then a 1. And there's my output, which right here it looks like they're the same, but if I actually cursor over it, I can see that the output is has a lot of rounding possible as well. I'm going to erase this parenthesis because I don't know how I'm going to get it fit all in. So 1.31 806 213. We better go out a little bit further because even to that many decimal places, these numbers look identical. So let's take this guy out a little bit. And go back up. 318061189. So we'll round it that far. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So now, by this time, as we go out farther and farther, the decimals start to look a little bit different. So 8.000001 is just a little bit bigger than this guy here. So we can see that we anticipate that the total number of voters is going to continue to increase, as we see in the pattern already. So now we're going to find the slope between them as we do the old-fashioned way. Rise over run, or change in output over change in input. And do that over 8.00001 minus 8 and see what we come up with. So I'm just going to come back to my home screen here. 1.31, whoops, 1.31806.213 minus 1.31806.189 divided by, well, the difference is going to be, I'm just going to do this in my head, 0.00001. That's how far horizontally these 2 points are. And I come up with a number that's about 0.024. So what does this mean? Well, remember, this is a slope that we found. It's pretty close to an instantaneous slope, but the units are going to be the units of the output, which are the total voters as a function of years. And so we'll have, and this is in 100 million voters per year. So this is our anticipated instantaneous rate of change, that there's going to be an increase of about 0.024 million voters per year. That's the old-fashioned way. Now, of course, that's really painstaking, but we know that we're going to get fairly certain results by doing it the old-fashioned way. Now the question is, well, how do you think you would find the derivative of this function, the product of these two guys? Now we have a product of a linear and an exponential. So a lot of people, here's what they would say. They'd say, hey, you know what? I'm just going to take the derivative of the first factor, which is 0.025t plus 2.1. So that's not the derivative yet, that's just the original, minus 0.09 times 0.86 to the t plus 0.6. They say, oh, you know what, I'll just take the derivative of this guy, which that's a linear function, so I know that's just going to be 0.025. Derivative of 0.025t is 0.025. Derivative of a constant is 0, and so that would be the derivative of the first term. So intuition says this. And then I'll take the derivative of this guy here. Now keep in mind, this is an exponential function of the form a times b to the u. If we look back at our formulas, the derivative of an exponential function is u prime ln b times a times b to the u. So the derivative of t is just 1. That's the power. We've got to use the power rule on this guy. Times the natural log of the base, which is 0.86, times a, which is negative 0.09, times b, which is 0.86 to the t power. Now, the derivative of a sum, remember, is this: we take the derivative of each term separately and then add them together. So the derivative of 0.6 is 0 because it's a constant, and we're left with this sucker here. Okay, so what would we do now? Well, what we would do is we would take, to figure out what t prime of 8 is. So in other words, using my equation, what's the instantaneous rate of change in 2008? Well, it would be 0.025 times ln 0.86 times negative 0.09 times 0.86 raised to the 8th power. So that's just evaluated at 8. Well, look what I get. I get 0.0001. Now, that's not what we got over here using this method. I got 0.024. So how can it possibly be that this, our intuitive way of just taking the prime of this guy and taking the prime of this guy, that doesn't give us the right answer. So this method, our intuition fails us here. So that's really what we're trying to build up. When you evaluate t prime of 8, does your answer match up with what you got in A? If not, what can you conclude about your intuition in part B? We can conclude that our intuition in part B, that just trying to think that we can take the derivative of each factor and then multiply it together, does not work. That leads us to something called the product rule. The product rule says that if you have a product of two functions, say f of x times g of x, we'll give this a new name. We'll call this h of x. So h of x, this new function, is generated by multiplying two functions together. Then the derivative of this guy would actually be, it looks kind of funny the first time you see it, but it's actually pretty easy to use. F prime of x, so take the derivative of f of x, multiply it by the original g of x, so don't take the prime of that guy, plus take f of x, don't take the prime of it, times the derivative of g of x. So the derivative of f times g plus f times the derivative of g. So both terms look kind of the same, except the prime goes on the other function. So in our case, in our example, we have 0.025t plus 2.1 times negative 0.09 times 0.86 to the t power, you can call this x if you want, plus 0.6. Now, if you look at this thing, we call this the total function. Here is sort of our, I'm going to make these x's for now, just so you're not confused by the notation potentially. So we'll just say this is x, and it represents the number of years since 2000. So then, if we call this guy f of x and we call this guy g of x, a really, really easy way to set this up is I'm going to need f of x and I'm going to need f prime of x, because that's what the formula calls for. So what's the derivative of 0.025x plus 2.1? Well, using the power rule, the derivative of 0.025x is 0.025. Derivative of 2.1 is 0. What's the derivative of g prime of g of x? Well, we do have to in fact use the exponential rule, which we wrote on the previous page to be the derivative of u, which is 1, times the natural log of the base, times negative 0.09, times 0.86 to the x power. That's the whole derivative of g of x, because the derivative of the constant is 0. So then we're saying that the derivative of the total function will be f prime of x times g of x plus f of x times g prime of x. Okay, so now all I have to do is I have to go and figure out what these pieces are. So f prime of x I have written down, that's 0.025. G of x is the original function, this guy here, negative 0.09 times 0.86 to the x plus 0.6, plus, there's more, f of x, which is the original guy here. I'll write this a little bit lower, 0.025 x plus 2.1. And g prime of x is its derivative, which is this big mess, ln 0.86 times negative 0.09 times 0.86 to the x power. So it's this big long mess. 0.025 times this guy plus 0.025x plus 2.1 times all of this, which is g prime of x right here. So it looks really, really terrifying, but keep in mind that all you have to do is leave it like that. You don't really need to simplify it. You can, but you don't need to. So let's just confirm. So what would we get using this new function, t prime of 8? Would it give us what our old-fashioned method gave us, which we said was going to be 0.024? Do we get something closer to that? Now keep in mind we still might have a little rounding error, but we shouldn't get something that's too far off. So I'm going to back up here. I'm going to take this function and I'm going to use my calculator to evaluate it at 8. So I just got to be careful in typing it in. 0.025 times negative 0.09 times 0.86 raised to the 8th power plus 0.6 close parenthesis plus open parenthesis 0.025 times 8 plus 2.1 close parenthesis open parenthesis natural log 0.86 close that parenthesis times negative 0.09 times 0.86 raised to the 8th power. Close that. So it looks terrible, looks absolutely terrible, but it is what it is. And check that out. We get out of this function the same thing that we got by doing it the old-fashioned way, well, roughly with some rounding error. So we get t prime of 8 is equal to 0.024, or approximately equal to 0.024, which is the same as the old-fashioned output. So that's really an important result here. When we notice a product of two functions, we want to apply the product rule. Simple as that. So that's basically a very important example of when you need the product rule. The product rule is anytime you have the product of two functions. Now I'll do the same thing. Let's look at a couple of examples here, just so we know how to do this. So let's just say we have h of x equals x squared plus 2x times x to the 4th minus 6x squared plus 3x plus 1. Well, again, intuition says take the derivative of this, multiply them together. we see already that that's not possible. So the first thing we'll do is we'll always say, okay, look, it looks like a product of two functions. I've got a quadratic and I've got a quartic here. It doesn't really matter which one you call f of x and which one you call g of x, because they're being added together. But I'll just call the first one f of x, the second one g of x. I'll next list out my prime of f, and using, this really is just a polynomial, so its derivative is 2x plus 2. G prime of x, its derivative is 4x to the third minus 12x to the first plus 3 plus 0. And now we note that the derivative of h is going to be the prime of f times g plus f times the prime of g. You don't have to write the h of x, f of x. It's handy to know what the independent variable is, but you can write it this way if it makes it a little bit easier. So f prime, I just come up here, I grab it, I plug it in, 2x plus 2. G is 4x to the third minus 12x plus 3. Plus f of x is x squared plus 2x. Times g prime, which is, I'm going to write this down here, 4x cubed minus 12x plus 3. And I'm done. You can FOIL, you can simplify, but there's really no reason to do that unless you really just enjoy doing that. You're maybe a glutton for a little bit of factoring punishment, but it's not necessary. Let's take a look at another one. We'll call it that example 1, and we'll do another example. So let's just say that we have d of t equals 0.5 times e to the x, or e to the t, times the log base 2 of x. Now we notice right away that we see there's a product, and we see that the product contains an exponential and it contains a logarithmic. So I know that there are two different functions being multiplied together. So the first thing I'm going to do is the same thing. I'm going to call this my f. Notice now I don't need to say f of t, because we know it depends on t. I'll call this guy my g. I need to find the primes of both of them. So f prime, well, this is an exponential function, so I've got to apply what I know about exponential functions, which the derivative is going to be u prime times ln of the base times a times b to the u. So my u is t, derivative of t is 1, natural log of b is the natural log of the base in this case. We know that the ln of e is 1, times a, which is 0.5, times b, which is e, raised to the u power, which is t. So there's my f prime. And I'm going to simplify that because I know this becomes 1. And so this can be really made to look very, very simple. 5 times e to the t. Do the same thing for my log. G prime is equal to, I know that the formula for the derivative of a log looks like this. It says, I'll write it off to the side here, a times u prime over u times the natural log of b. Okay, well here is my base. Well, what's my a? A is the coefficient out front. Since I don't see anything, I can say it's a 1. Oh, that's a 1 there, excuse me. So this is my value of a. Here is my, we're calling the u. So a is 1 times the prime of x, which is the derivative of x is 1, divided by u, which is x, times the natural log of b, which b in this case is the base of 2, ln 2. And so, just kind of cleaning this up slightly, we get 1 over x natural log of 2. Now I can just really plug it into my formula. D prime of t is equal to, it's going to be f prime g plus f g prime. F prime, we said, was 5e to the t times g. Well, g is the original undifferentiated version of g, which is log base 2 of x, plus f, which is 5e to the t, that's the unadulterated version, and times g prime, which g prime is 1 over x ln 2. Sorry, I'm sure you do this as well sometimes. Instead of using your x's, you use t's. Instead of using t's, you use x's. So it should actually all be t's here. Alright, well that's it. That's how we use the product rule. We can basically use any two functions and multiply them together, and this same rule applies in the same way. So stay tuned for the next video for Quotient Rule.